Welcome back to the Math Professors. If you enjoy content that can be found in the college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover how to determine if a set is a subspace. So U is a subspace of vector space V if for all U and V in this claimed subspace and scalar C that it is closed under vector addition and also closed under scalar multiplication. Now these are vectors, and a lot of times we'll write arrows above these things to verify that these things are vectors, but we're just going to assume vectors, so I'm not going to write arrows every single time. Okay, so what I have is two examples, and we'll do a couple ones after this. This is a 2 by 2 matrix, and I want to know if this is a subspace of, I want to know if this is a subspace of all 2 by 2 matrices. So, a subspace of this. Now, in order to prove something's a subspace, I just have to prove that it's closed under scalar addition and also, vector addition and scalar multiplication. So let's check this. So what I'm going to do is I'm going to have to define a U vector and I'm going to have to define a V vector. So, and they have to be of this form. So U is going to be, I'll do U1, U2, U3, and then 0. We can see it has the same form because it says to be in this vector space, A, B, and C are real numbers. Only the last element has to be equal to 0, and that's what I have here. And then vectors V is going to be equal to, let's just do V1, V2, V3, 0. It's nice to define, everything is U's and everything is V's, so then when I want to reorder these things, it'll make a little more sense when we're trying to determine structure. All right, so let's check. Check property 1. So property 1 being this. So U plus V would be equal to, when I add two 2 by 2 matrices, I just add their common components. So this is going to be U1 plus V1. This would be U2 plus V2. U3 plus V3, and this will be 0 plus 0. Now the only thing I need to verify is that these things are real numbers, and we can tell that 0 plus 0 is nothing more than 0. So this is an element of U because it has that form. The next thing I have to check is scalar multiplication. So 2, what about C times a vector U? Well, this will be C times U1, U2, U3, and 0. And when I multiply this, we know when we multiply a scalar times a 2 by 2 matrix, you just put the scalar to every element. So CU2, CU3, and this would be C times 0. Now, very similarly to what we had before, this was 0 plus 0 is equal to 0. Now, C times 0 is equal to 0. And what I can say is that this is an element of U, because again, real number, real number, real number, and 0 here. Now, I want to determine if this is a subspace. So, again, of all, 2 by 2 matrices. So first we're going to check property 1. Is it closed under vector addition? So I'll have to define a U first and then a V next. So U is going to be equal to U1, U2, U3, and 1. And then our V vector is going to be equal to V1, V2, V3, and 1. So now checking property 1, is it closed under scalar under vector addition? So when I add these two matrices, we're going to add their common components. And then this will be equal to 1 plus 1. And it's here that we have a problem because remember, to be of this form has to be real number, real number, real number, and this has to be the number 1. But 1 plus 1 is equal to 2, and that means it doesn't have that form. So this is not an element of U. So this is not closed under vector addition. You could also prove it's not closed under scalar multiplication, because if I multiply this thing by C, this would be equal to C and not equal to 1. So it'll fail number 2 as well. But to fail 1 is enough. All right, so two more examples. Now, this would be a subspace of, say, R3, because what I have is I have a three-dimensional or three-component vector. And this would be of a two-dimensional disk. So this is going to be of R2. So I want to see if if this is closed under a vector addition and scalar multiplication, and I'm going to check this one as well. So we'll do one at a time. So first, I have to define a U vector. U is going to be equal to, let's say this is U1, comma U2, and this would be 2U1 minus 3U2. Again, what I like to do is if I define a U vector, I like to use U's in these spots. They don't have to be S's and T's. So then V is going to be the same kind of idea. Say V1 first component, V2 second component, 2V1 minus 3V2. Now when I want to check that first property, is it closed under addition? U plus V. When I add these two vectors, I'm going to add their common components very much like matrices. So U1 plus V1. And then this will be equal to U2 plus V2. And then I'll have, this addition, 2U1 minus 3U2 plus 2V1 minus 3V2. Now our job is to say that it's of this form. So, if this is some vector S, then I need this to say, 2S. So whatever is here, it has to be double whatever that thing is, and then minus triple whatever this thing is. So, this is acting like your T S, and this is acting like your T. So what I want to see over here is I want 2 of these minus 3 of these. So I'm going to reorder this, and we can see that that's going to happen. So if I pull the 2's, this is 2U1 plus 2V1, and this will be minus 3U2 minus 3V2. And now what I could do is I could factor a 2 out of here, factor a negative 3 out of here. So what we'll have 2 times U1 plus V1 minus 3 times U2 minus V2. Sorry, plus a V2. And then we can verify that we indeed have 2 of these minus 3 of these. So this is an element of U. Now we also have to check for scalar multiplication. So C times U. Well, this would be C times U1 comma U2 comma 2U1 minus 3U2, and then when I distribute the C across here, well, it's going to be CU1, CU2, and then it's going to be C times this what is here, so 2U1 minus 3U2. Now what I want this to say again is I need 2 of these, I need 2 of the first minus 3 of the second. So when I distribute the C in here, I'm going to do it cleverly. I'm going to put the C just in here. So this is going to be 2 CU1 minus 3 CU2, and that's what I have. I have 2 of these minus 3 of these. So we can see that it still has that correct form. So this is an element of U. So this is closed under vector addition. Let's try for this one. So again, I need to find a vector U and a vector V. So it's kind of our choice since I only have one T. So let's just use U. So let's say U would be equal to 2U plus 1 comma 3U. Since I only have one dependent variable essentially, I don't need subscripts. I use subscripts here because I have 2 dependent variables. I have 2 things over here. So since I only have 1, then we're good. So V is going to be equal to 2V plus 1, 3V. So now I have to test, the first property. Is it closed under addition? So let's say U plus V is going to be equal to, when I add these two vectors, this is 2U plus 1 plus 2V plus 1. And over here I'm going to have 3U plus 3V. So I'm gonna reorder these 2U plus 2V and then plus 1 plus 1. And here what I would like is I just pull out that 3, because remember what I'm trying to show is I'm trying to show that it's 3 times this this particular this T value. So U plus V. Now over here if I factor out 2, I have that U plus V. So it does look like 2 times that particular variable like I have here. But unfortunately when I do 1 plus 1, I get 2 back. Remember, what it's supposed to be is 2 times something plus 1, and then 3 times that same something. So I have that 2 times something plus, well, 2. And then that 3 times something. So this component here was fine. This component here is not because of this 2. It's supposed to be a 1. So that means that this is, this is not an element in U. So this is not a subspace. You could also show that it likely is going to fail for number 2, but it just has to fail for one of these. So, this is not a subspace. So there's some properties of R that we can discuss on how to determine if something's a subspace. So for instance, right here, what we have is we have a line in parametric form. But if I have R2, if I need this to be a subspace, if it's a line in parametric form, it has to run through the origin, and this doesn't. Like, for this to run through the origin means that, this piece right here would have to be equal to 0. And the only t value that would make that 0 would be 0, so 3 times 0 is 0. But when I plug 0 in here, I'm going to get 1. So, this doesn't run through 0, 0. Now, over here, this is an R3. So again, to be a subspace in R3, it would have to be linear in R3, so we're talking about, either a point, a line, or a plane. And since I have two dependent variables, well, this is actually a plane. And it's a plane through the origin because the only way to make these things 0 is if S and T are both 0, right? And, so get out of your way, all this red. So if these are both 0, then this would also be 0. So this will run through 0, 0, 0 when S and T are both 0. So this right here is a plane that runs to the origin. So if we're talking about R3, things that look like things that are subspaces of R3. So if I have, 3 dimensions here, things that are subspaces of R3. So this would be, an X, a Y, and a Z. Well, one thing that would definitely be a subspace of R3 is just, the 0 vector. So if U is just equal to 0, 0, 0. That would be a subspace. It would be closed under addition, scalar multiplication, and so on. If I have a line through the origin, let's try to make that happen. Missed it. If I have a line that goes through the origin. So this might be, it just has to be of one dependent variable. So maybe S and 2S and then say 5S or something like that. That would be an example of a line going through the origin. I can guarantee that would be closed under addition and scalar multiplication. I could have a plane through the origin. I'm going to make sure that it's crossing that origin here. And this is an example of that. Or you could have the entire space. So you could also have R3 itself. So U being, a subspace. So, this being a trivial subspace, this also could be the trivial subspace. These two being more interesting. Now, if I'm talking about R2, well, R2 has a very similar property as well. If I want it to be a subspace, it has to be, essentially linear through the origin. So there are 3 of them. We'll see. You could have just 0. So 0, 0 would be a subspace of R2. Could have a line through the origin. So something like, let's make it go this way for fun. So if I have U is equal to, minus 2t, 3t, or something like that. Notice that the reason why this one broke is because of this 1. This doesn't have that 1 now, so this will definitely be a line through the origin. So it'll be a subspace, you can check it. Or you could have the entire space. So you could also have R2, so if U is itself. So those are the kind of types of subspaces you'll see in ours. If you like the content, please subscribe.